Good afternoon, class. Today we are going to be talking about transformers. So when the power is generated in a big generator, such as our hydro dams, the voltage that it's generated at is pretty high, but it still gets ramped up to the hundreds of thousands of volts. So it gets ramped up even higher for when we're going to be transmitting it long distances. Now you might wonder, why should we transmit it at exceptionally high voltages? Is because there's inherent resistance inside of power lines that result in energy loss. And so we can tell that if you're paying attention to Ohm's power law that you might remember from grade 11, that high voltage means that there would be a low current, right? Power is equal to V times I. So for any given power, if we have a high voltage, that means for a low voltage. So the power loss follows this formula. Now you might also remember Ohm's relation relating voltage, current, and the resistance. The resistance in the wire is constant because those wires aren't changing so much. So if I substituted IR in for voltage, we'd see that power is equal to current squared times resistance. So this would be power loss due to the current squared times the resistance. And if I reorganized Ohm's relation, I is equal to V over R, substituted that in, we'd see the power loss due to the voltage is the voltage squared divided by the resistance. Hopefully, noting that any resistance greater than 1 ohm, and if you're dealing with any cables that are kilometers long, you're definitely dealing with resistances greater than 1 ohm. You hopefully would recognize having if you choose either high voltage or high current, you notice that the high voltage would result in a less power loss in total because it'd be the high voltage squared divided by that resistance. So you divide by the resistance of your system to determine how much power loss you have. So really it means that transmitting in the highest voltage that you can would result in the least amount of power loss. And when we're producing and transporting energy, obviously the less loss that we have, the better. But these hundreds of thousands of volts might set our homes on fire, so we probably want to bring it down to a low voltage. How do we bring these high transmitting voltages down to our low 120 volts for North American standard, and I think it's 220 for Europe standard? How do we bring those high hundreds of thousands of volts down to a reasonable home use? This requires a device called a transformer. A transformer is made of two coils, one called a primary coil and the other called the secondary coil. And they're wrapped around a shared core, usually made of some ferromagnetic material, allowing for an easy transfer of magnetic field. The current flowing through the primary coil produces magnetic fields, as we've seen, right? Magnetic fields. And these magnetic fields, the core helps them travel through this space in between the primary and secondary coil, hopefully with minimal loss, and the magnetic field through the secondary coil can then induce a current in the secondary coil. But you might say, Mr. Westgard, hold on. To induce a current, you don't just need a magnetic field, you need a changing magnetic field. And so how do we do that? How do we make this magnetic field constantly changing? You might remember that we actually produce our electricity with our rotating loops through magnetic fields. That produces alternating current. Alternating current is constantly changing current, which means the magnetic field produced by the primary coil is constantly changing, and this constantly changing field is moved through the core into the secondary coil. So that means we have a constantly changing field in the secondary coil, which is going to create a constant the changing magnetic, or constantly changing current through the secondary winding. AC through the primary winding gives us AC through the secondary winding. It's very convenient. We don't even need to do any AC to DC changes for this. It's just keep it all as AC, and the fewer changes we have to do, the higher the efficiency. So it's quite nice. Now, how do these two different coils relate? How do they relate in terms of their EMFs? Well, the EMF of the primary coil would be found through a relation N of our primary coil multiplied by the change in flux over the rate of time. And the EMF of the secondary coil would be the number of coils in our secondary loop by the change in flux over time. And ideally, if this core is working perfectly efficiently, the flux running through the primary coil should be equal to the flux running through the secondary coil. So these should be the same. And the rate that the current is flip-flopping in the primary coil determines the rate that the flux is changing, so the change in times should also be exactly the same. So since those are the same, if I wanted to determine the ratio, what's my relationship between the EMF in my primary coil and my EMF in my secondary coil, I would simply divide by what they are, their formula. NP, change in flux over time, over, and secondary, change in flux over time. But since the change in flux and the time are the same, they just cancel out. Huzzah! And so we can see that the ratio of the primary and secondary coil is directly related to the ratio of the EMFs from the primary and secondary coil. So let's get that down in our happy little formula box here. The ratio of the number of coils is directly proportional to the ratio of the EMFs, or the voltages. But even though you're changing the voltage, there is a fundamental law that we have to follow. You have to conserve energy. And so that means, well, since we're not actually measuring energy, we're actually going to be checking power, because power is just the rate of change of energy, should be the same for both sides. So the power in the primary coil should equal the power in our secondary coil. Now if we go back to that Ohm's power law that we had from before, the voltage in our primary coil multiplied by the current in our primary coil should equal the voltage in our secondary coil multiplied by the current in our secondary coil. We could make a similar set of relations as we did before. V primary over V secondary, that's just the same as our EMFs, would be current secondary over current primary. So we see while the number of loops ratio is directly proportional to the EMF ratio, it's actually inversely proportional to the current ratio. So whatever change you make between the primary and secondary loops, make the same proportional change to the EMFs, but do the reverse or the reciprocal relationship to the currents. And this will allow us to conserve energy, because you always have to conserve energy. It's the law. This means that we generally can break down our transformers into two broad categories, step up and step down. When we do these, we are almost always referring to their voltages. So the step up transformer takes the secondary voltage and makes it higher, or a step up from the primary voltage. This means that there's going to be more loops in our secondary coil due to that direct proportionality. So if I'm taking a look at this situation, I see I have 5 terms in my primary to 20 terms in my secondary. I chose the numbers to be easy, so I didn't need to show my work. If the numbers aren't so easy, just show your work, write down the ratios. But in this case, 5 to 20, that's a 1 to 4 ratio. So we see that there's an order of 4 change. So 100 volts is my EMF through my primary loop. What's my EMF through my secondary loop? It is the same proportional change. Going from 5 to 4 is at times 4, so 100 times 4 would be 400 volts. So we should see 400 volts through of EMF through the secondary coil. That is a big step up. But since we have to conserve energy, we notice that our current is going to go through the same process, but instead it's going to step down. Instead of multiplying by 4, the primary current gets divided by 4. So 10 divided by 4 becomes 2.5 amps. And so this is the case of a step up transformer because the voltage gets stepped up. Very clear. Very clear. The step down transformers, they make secondary voltage lower than the primary coil. This means that there's going to be more loops in the primary coil. So we see our same situation with our primary and our secondary, or our primary voltage and our primary current, or our primary EMF and primary current. You see this is a 50 to 10 relationship, or a 5 to 10, or a 5 to 1, 5 to 1 relationship there. And so our EMF is going to be stepped down by a factor of 5 in our secondary. So 1000 less 5, or divided by 5, is going to be 200 volts, quite a bit less. But on the flip side, the current does the reciprocal relationship, so instead of being divided by 5, it is multiplied by 5. 2 by 5 turns it into 10 amps. That's going to be it for our lesson on transformers.
Autobots, transform and roll out!
Have a good day.